Seonghyeon.
Hi everyone, I'm Seonghyeon Park from Hostel. As my advisor Seonghyeon Park could not attend, so I will make presentation instead. Here is the topic of my presentation: artificial intelligence generation for enhanced circuit data computation. Here is the outline of my presentation. I will start with some background and motivation, and then move on to talk about the knowledge generator. Here I will talk about the two applications of knowledge generator: timing and route-based optimization. Then I will present RTR code augmentation method for large language models, and end my talk with conclusion and future directions. Let's start with the background and motivation. These days, designing a chip costs more than $500 million. As we know, this design crisis comes from the massive increase in turnaround time. Given these challenges, ML can be a game changer for improving the efficiency of traditional EDA workflows. With ML techniques, we can predict design quality metrics like timing and routability, allowing us to prune the best designs by space without running a full k-NARC load. Plus, we can leverage these predictions to enhance design quality even further. However, real chip design data is sparse and expensive. That's why synthetic data has been widely used in ML research to overcome the limitations of real-world data. Key advantage of synthetic data is that it can create complex scenarios that real-world design cannot easily provide, making it useful for training ML models. In this talk, I will focus on three key EDA challenges: timing optimization, routability optimization, and RTL generation, and how synthetic data generation can enhance this ML-based EDA flow. Let's first talk about data types that we can use in EDA. Synthetic data in EDA comes in many forms, but in this talk, I will focus on two: gate-level netlist and RTL code. Let's start with gate-level netlist. First topic is about the netlist generator for timing optimization. In the traditional EDA flow, various optimization techniques like buffer extension, gate sizing, and VT swapping are used. Typically, these methods are applied separately prior to checking timing closure. If it is not achieved, the process starts from the beginning. Then, this iterative approach leads to suboptimal timing optimization. Sizing problem is very well studied, and a lot of sizing methods are available. But there's no systematic way to say which one is better or how suboptimal they are. Other unanswered questions are whether one of the heuristics is better for a given circuit topology or library characteristics. The motivation of iChart is to answer these questions. Professor Gupta proposed chain, mesh, and star-shaped topology. Each can be solved optimally, but its diversity of topology was restricted. To evaluate suboptimality of sizing heuristics, more realistic benchmarks are required along with fluid generation flow. Professor Kang proposed benchmark circuits with non-optimal solutions for gate sizing. The proposed benchmark resemble real designs in terms of gate count, path depth, length parameter, and depth degree. With a realistic benchmark, they have evaluated the suboptimality of standard gate sizing approaches. Imagine if we could generate a netlist with non-optimal solution. Your model could learn directly from it. Now, can this model predict the optimal solution for real-world design? The problem is with existing ML-based sizers is that they are trained suboptimal solution. But if we have to If we were to have access to optimal solution and use them as labels, we could train much better ML-based sizer. Our future work will include this sizer. Second topic is about the list generator for routability optimization. Routing quality is typically evaluated at the end of physical design flow. So if routing failure occurs, more iterations are needed, leading to longer design turnaround time. ML can solve this issue by learning the relationship between routability and layout data after placement. An ML model can predict routing congestion or DRB hotspots. This allows us to reduce design time by creating a shortcut as shown in this one. Here, we introduce artificial list generator, ANG, to tackle the lack of shareable PNR data. The recent development of ANG can be a potential solution. It offers a systemic approach to create artificial yet realistic PNR benchmarks. It uses various topological and layout parameters such as instance count, IO, net characteristics, path characteristics to create realistic net list. The figure shown here illustrates the PNR data generation process using ANG. These slides illustrate how ANG can be used for DRB optimization flow. First, we train an ML model using an ANG augmented dataset. Second, we use the model to predict DRB heat map. Next, we generate a contribution score map using X-Level AI to identify key features responsible for DRBs. Finally, we apply optimization techniques based on these identified key features. In our experiment with 3 different designs, this approach reduced the number of DRBs by an average of 50% compared to the default design flow. Now, let's move on to RTL code synthetic data. This research on LLM-based RTL code generation will be presented at the coming Date 2025 conference. With the growing interest in LLMs, there has been a significant push to apply them in the EDA field. This chart shows the number of papers related to LLMs presented at EDA conference over the past 2 years. It shows a strong and continuing trend toward integrating LLMs into EDA. In this talk, we will discuss LLM-based RTL generation. The key challenges in optimizing LLMs for value code are data scarcity, prompt generation, and fine-tuning methodology. Among these studies, we will focus on data scarcity. Value code is often classified as intellectual property, making them unavailable to the public and open source datasets scarce for training LLMs. Therefore, we propose an AST-based augmentation method to generate diverse value code. This approach helps mitigate data scarcity by augmenting the training dataset. An abstract syntax tree represents a program's synthetic structure as a tree, where each node corresponds to a construct or operation that defines the program's logic. By modifying the AST structure and converting it back into code, we can generate augmented code to enrich the training dataset. For AST-based augmentation, we apply 3 main techniques: modification, insertion, and deletion. For modification, we swap a node with another of the same type, keeping the overall AST structure intact. For insertion, we add new nodes beneath the leaf node, making the AST deeper. For deletion, we remove a target node along with its children and clean up any unused variables. Here is an example of AST-based code augmentation. can generate right one. Here, we can see insertion, modification, and deletion applied to transform the code. We evaluate the impact of data augmentation by training the baseline model on 3 different datasets. One with 10,000 real dataset samples, another with 10,000 AST-based data samples, and a third combining both. The left graph shows the result on RTLM benchmark, while the right one is from the Verilog eval benchmark. In both cases, the combined dataset performed the best. This confirms that AST-based augmentation effectively improves LM's performance for Verilog code generation. Now, I will conclude my talk with remaining challenges and future directions. For timing optimization, NetGen, which generates optimal net list, has its own strengths and weaknesses. Net lists from NetGen are specifically fitting for contest benchmark, which makes them less applicable to real-world designs. To overcome this, we need to reduce the gap between real and artificial design and incorporate realistic delay models to improve practical applicability. For routability prediction, AMG has limitations such as the lack of macro consideration and difficulty in handling large-scale designs. To overcome this, future work should focus on supporting macros, enabling hierarchical design, and generating large designs more efficiently. Last, for RTL generation, AST-based augmentation often lacks functionally consideration and is high dependent on the original RTL dataset. To address this, we need techniques that incorporate functionality constraints, ensuring that augmented RTL is not only synthetically diverse, but also functionally meaningful. This completes my talk, and I'm open for questions. Thank you.
Questions from the audience? Don't be shy. Got some time. Questions? So I have one. It challenged the slides of one also. For example, with reducing the gap between real and artificial design, would it be a problem if we don't actually have the realistic delay models, for example? Then kind of maybe we're never able to generate a realistic net list in terms of timing, because we never see the extreme cases the realistic model would see.
Yes, legend is still have some gap between realistic unseen data and its own list. So our future work, we are going to reduce the gap between these designs.
Yeah, just it's more in the sense that